Hey everyone, I think we can get started. So give me a minute. Sorry for the delay. I think the host forgot to start the meeting, so even I was not able to access anything. So yeah, so I discussed with the thing regarding the last session where we had some confusions on various batches in a single thing. So I think it might have been communicated, but I thought I'll also communicate from my side. So what we'll be doing is, I think majority of you are new here. So we'll be starting from the first for you guys. A few of them would have already attended this session. So if you feel bored or if you feel, if you want, you can feel free to listen to it again. If you don't, it will be kind of similar. Tomorrow I'll try to change something, and not tomorrow. The next session I'll try to change something, but it will be kind of similar. If you want, I can give you some problems for people who already attended. For people who are new, we'll be studying from the first. So that's what you're going to do. So I'll share my screen. So any doubts in this? Okay, great. I think we can get started then. If you remember in the last session, we were discussing few questions and we were writing something, right? So we had many approaches, and every approach I was writing something nearby, right? Say in a given question, so for a given question, you have four approaches. So how do you know that, okay, one is better than the other, right? So that's what we are going to see. So in our previous case, uh, the sorting was kind of better, right? Sorting was easy to do. You just sort it, you do it, right? But even though it was easier to do, it is not the most efficient approach, right? So how am I saying that, right? So that's what we'll be seeing. So if you see here, right? So I'll try to share this slide as well. I mean, sorry, this link as well. Okay, just give some name and I'll give this link as well. So if you see here, right? So we had four approaches. So this problem is you'll be having an array where all the elements will be repeated twice except one. So you have to say which one is repeating only once, right? So even though the sorting was easier to understand, it is not the most efficient approach. The caret symbol we used, right? The XOR was the easiest approach. So how am I saying this? How can I say one is better than the other, right? So that's the main idea of time complexity. So for a given problem, there will be multiple approaches. But how do I know, okay, this approach is better than the other, right? So that is where, that is where you use time complexity. From an interview, what does it mean? In an interview, you can come up with some approach, right? But unless you come up with the most efficient approach, they'll not allow you to go. So that's the basic idea. So what does it mean is, say you're coming up with some approach here, okay? That approach is not the most efficient approach. So how do I know this? So you can find the time complexity of approach A. Interviewer will be having some approach, some time complexity in his mind, in his or her mind, right? So that is the most efficient time complexity. Right? Unless you come up with an approach which is having the same time complexity as the expected, you will not be allowed to code. Right? So the thing is, it's not that you have to do it in the same approach. You can do it in any approach, but as long as the time complexity expected and time complexity of your approach are matching, they are fine. So you're clear, right? So there can be even 20 approaches where the time complexity is the most efficient, right? You can come up with any of those 20. As long as you come up with the most efficient time complexity approach, you will be allowed to code, right? So till that point, they'll be, asking you to improve your solution, right? So most of the companies will not allow you to code unless you come up with the most efficient solution. So how do I know that, okay, given a solution, given a question, I know, okay, this is most efficient, right? So first is practice. So usually after you practice some things, you will be able to understand, okay, I'm doing something wrong or I'm doing something over unnecessary, right? So whenever you do some unnecessary things, you are going to spend some unnecessary time, right? So that is a basic idea. So today we'll be seeing only, what is time complexity. This is more of a theoretical session. So as I said, if people who have already attended 2 weeks back, I guess. So if you want, I can give you some problems. If you want to listen also, I'm totally fine. Okay, so we'll get started with time complexity first, right? And we'll try to understand, okay, what is the use of it, and how do I find the time complexity? Right. Okay.
போய் பூ எடுத்து வருவேண்டா சாமி கச்சு விடுறதுக்கு கீழே கீழே இருக்கா போய் எடுத்து வருது அதுதான் கூப்பிட்டு.
Okay. So first we'll be understanding what is time complexity. Right. Okay. So first we'll see what is the issue with using time as a way to understand a program, right? So say say you have a code. So this code is say C. You take a code from the internet, and what you're going to do is you're going to run it in your machine, and your say B is your friend. This B is going to run in his or her machine, right? So this code you're going to just compile and then see how much time it is taking, right? So that's the basic thing we are going to do. So what you're going to do is, so say you're having a very old machine and your friend is having a very new machine, right? Like faster processor, more memory, and those kind of things. Yours is kind of old, say 5 years, 6 years old, right? So definitely for a given task, your machine will be slower. Okay. So you take a code from the internet, and what do you do is you run it on your machine, right? And you find the execution time. So what is the execution time in a piece of code? So you'll be giving the input, right? And after you give the input, there'll be some time delay, and after that the output will come. Say for example, login page, right? So you give the input, email ID and password. From the moment you click login till the moment it is signed in, that part is execution time. How much time it is being executed, right? So this is a very common term in computer science. So execution time is just that part, not the part where you give the input or do something with the output, right? Only the mid part, where the moment you give the input until you get that output, that part, right? That's that execution part. So, right. So that is called the execution time. So what you're going to do is you're going to take a code. You're going to give the same input, right? You are going to give the same input X. Your friend is also going to give the same input X. You'll be getting the output Y. Your friend will also be obviously getting the output Y, because it's the same piece of code, right? So this is what you're going to do. And you're going to calculate the execution time in each of these cases, right? So you'll be having some execution time A. Your friend will be having some execution time B, right? So you're going to compare EA and EB, right? Okay, so is everyone clear on what you're going to do? Taking a code, running in each of your computer, and finding the execution time. Okay, so I hope everyone is clear. If not, you just let me know. Okay? So in between, anywhere, if you have any doubts, or if you are having something, so yeah. Okay, so I think runtime is also same, I guess. So yeah, runtime, execution time, both are same. Okay, so now, right now you're going to compare EA and EB, right? So you're kind of surprised that EA is less than EB, meaning your computer finished that task faster than your friend's computer, which shouldn't be the case, right? Because your friend's computer is much more faster, much more equipped, and compared to your computer. So now you're shocked that you're getting something in the reverse, where your machine was slower and your friend's machine was faster, right? So sorry, your machine was faster and your friend's machine was slower, right? So this is where you're kind of getting stuck, right? So after some analysis, you find that when you were running your piece of code, nothing was running behind the scenes, meaning you switched on the computer, you let it some time for it to settle down, and after that just ran this piece of code, right? But B, on the other hand, what he or she has done is, your friend, he or she was running a very high level, high intensity task behind the scenes. Say he or she was running a uh, high processing, like AutoCAD or something, or even high processing, the applications, right? Like Photoshop or something, right? Or some video editing software, right? So what has happened is the amount of resources available for this piece of code was very less, right? So it was already kind of switch more in a like overloaded. It was already overloaded, and on top of it, we added one more load, right? So that's why the computer was not able to So that's why the computer was not able to, kind of execute it faster, right? So now what is the issue, right? What is the, so so this execution time is not a very good way to understand how fast the code is running, because for the same piece of code based on the machine, there are two different things happening here, right? So yeah, so you get the difference, right? So this time is not a very good way to understand. So you can't say, okay, this guy is going to definitely finish in 1 second. B is going to, so you can't say that this piece of code is always going to take 1 second, right? So based on when you're running, where you're running, where is the computer, when is the time at which you're running, whether it is already overloaded or whether it is free, etc. Those kind of things, right? So yeah, so that's when they realize, okay, we should find something which is independent of all these, right? Because what you want is just the efficiency of the code. But here, this time is dependent on various other factors as well. As I said, when and where it is run, right? So that's why, time means time in seconds or time in some form, right? Some quantifiable form is not a very good way to understand, okay, this piece of code is running at this time or something. So we want to find a thing which is independent of all this. So is it clear, like why time is not a very good way to understand things? Right. So now they want to find something which is, independent of all this, right? So that's when they realized what is something which is going to, remain constant irrespective of the computer test at which it is run, right? So I hope everyone is, having basic knowledge on programming, right? So if you do, you know what is this for loop, right? So you know what a for loop is going to do. Say this for loop is going to run I from 1 to 100, right? So what this for loop is going to do? So just assume that 100 is also included. So it will run 100 times whatever is here, right? So whatever is here, this will be run 100 times, right? So that's the idea of this for loop, right? So will this run more or lesser number of times based on the machine? So if the machine is faster, will it run lesser number of times, more number of times? Right? So now you get the idea, right? So the number of executions a piece of code is going to take is independent of all these things except the code, right? So what is the number of executions? So here, whatever is inside this will be executed 100 times, right? It is a number of execution, right? Not the time it takes. Number of executions or number of instructions, right? So it is going to execute 100 instructions, right? 100 times this instruction, right? So you get the idea, right? So this is independent of everything except this. Except this, right? Okay, I think I didn't give you access for this word, I guess. Give me a minute. Okay, so you get the idea, right? So this is where they came up with an idea of this time complexity. Even though the name is time, it's not going to use time as such. It is going to use some other way to understand this, but you get the idea, right? So if you kind of find some function which is going to, give you, time complexity, which is going to give you how many instructions a piece of code is going to take, it will be dependent only on that piece of code. If there is some other code which is going to take more instruction, or it is going to take more executions, it will be slower, right? So yeah, so that's the basic idea of this time complexity, right? So the main idea is, given the same mission, if the environment is same, what is the only thing which is going to change? The way you write the code, right? So yeah. Okay, so this is the basic idea of this time complexity. So any doubts so far? Okay, so now once you're done with this, so now we have to see how to So how to, represent this, right? So for time you have seconds or milliseconds or something, right? So you have some representation. So what will be the similar kind of representation here, right? So yeah, so that's the basic idea here. So we have to somehow represent it, right? So first we'll see how to represent these things. Okay, so please use this link for that slide I shared. Okay, you don't need any permission, so from now on. Okay, so now you have to see how to represent this thing, right? Okay, so that's where we have some notations. I'll not go into all these notations. I'll just say which notation is being used everywhere, right? So there are other notations as well. Okay, so there are many notations, so we'll just take one notation, right? Okay, so to understand that notation, we'll just take some real world example, right? Okay, so now say you're designing some system, right? So there is some system which you're going to design, right? So this system, you know how many customers are going to come in here, right? Say Netflix, right? So you just take the system as Netflix, right? So you all know, right? So on September 5th, Money Heist, the latest season is releasing, right? So what is this Netflix will be doing right now is they'll be seeing how many customers can potentially come on that 5th September alone, right? Because a lot of people will be online at that time, right? Compared to today. So if you go, say there are 1 million people online now, okay? On 5th September, they say they're expecting 5 million people, right? So even this can be, kind of scaled when needed, but you need to have some number, right? You can't keep this 1 million and suddenly scale it to 6 million or something. It's going to break, right? So usually what do they do is they scale up to some expectation. If it is lesser than the expectation, no worries. If it is more than the expectation, they'll kind of tweak it, right? So this is in real world. But for our example, we'll consider that it can never go more than 5 million, right? So the max cap is 5 million. Okay. So say there are only 5 million customers, so it can't go more than 5 million, right? So yeah. So usually it will be 1 million, but on whenever a new series, a popular series is releasing, we are going to scale it to 5 million, right? So that's the basic idea, right? Okay. So yeah, so now say you are the designer of the system, or you are going to do the ops, you are the ops engineer here, right? So say it is September 4 already, right? So will you scale it for 1 million or will you scale it for 5 million if you want to handle the load? So 5 million people are going to come in tomorrow, right? So will you keep it as 1 million or make it as 5 million? So why do you do that? Right. So why do you scale it to 5 million compared to 1 million? Right. So 5 million is the max cap, right? So 5 million is the max cap, right? Or 5 million is the worst case, right? What is the worst that could happen? All the 5 million people are online, right? So that is the worst that could happen to your system, right? So this is the worst case, like this. Right. So you get the idea, right? So in time complexity, there are multiple notations, but there is some notation called O, right? So you say so how do you represent, what do you do inside this? I'll say in a bit, but this word O says that the time complexity can never be greater than this value. So there will be some value here. How do you get that value? We'll see. But what is time complexity saying is, say you're saying big O of some value. What is time complexity saying is the value uh, can never be greater than this value, right? So the time complexity can never be greater than this value. So that's the basic idea of this big O notation, right? So yeah, so we'll be using this big O. So how do you represent this and other things? We'll see in a bit, but you all get the idea, right? So there are multiple notations like sigma and theta. So but big O is the one. which is going to, give you the worst case time complexity. And you all know why you need only the worst case, right? So once you are covered for worst case, it will handle all the other cases as well. So you're kind of safe there. So any doubts so far? So especially the people who are attending, who are new to this, is it clear? Okay, so I hope it's clear. If you have any doubts midway, please do, stop. Okay. Okay. So now we are going to use some big Go and we are going to use some value inside. Right? So how to come up with this value, right? So for that, we need to understand a few things. Say you are writing a for loop, right? So I'll just take an easy example, 1 to n. Okay. So what does it mean? It is going to start at 1 and going to go till n. And there are some instructions which are going to happen inside this, right? So yeah. Right. So I'll kind of use this value to find this. Okay. So to kind of repeat this big O notation. Okay. So there is a for loop which is going to go from 1 to n, and it is going to have some instructions inside this, right? So what? So how do you represent the same in time complexity, right? So how many times this is going to be executed? So this instructions, how many times it is going to get executed? N times, right? So this execution is instruction is going to get being executed n times. So how do you do the same notation? It is O of n, right? So this is a basic idea on how you are going to use this complexity, right? So say a program is being executed n times, you're just going to write it as O of n, right? But it is not as simple as this. There are a few rules and other things which you have to see, but you get the idea, right? So what does this big Go of n means? This piece of code can never take more than n iterations or n executions, right? So n is the worst case time complexity of this piece of code, right? So that is why it's called O, and within that you are putting as n. So O of n is the worst case time complexity of this piece of code. So this piece of code can never be executed more than n times, right? So that is the basic idea of this notation. So for people who wanted me to repeat the last slide, are you clear? What is this big O and other things? Why it is big O and not the other notations? Other notations we didn't discuss, but this big O itself is enough, meaning it can never go more than n iterations, right? So if n is 100, you will not be executing more than 100 times, right? So n is the worst case time complexity. Right. So this is the basic idea of design complexity, but it is not kind of easy, right? So there are few things which we want to see to understand a few parts of this time complexity, right? So yeah. So whenever you have doubt when the slide is on, please do ask at that time. So yeah. Okay. So now we'll see two rules of this time complexity, right? So what are these two rules time complexity saying, right? Okay, so we'll just take the same example, you and your friend. So now since you and your friend know how to do time complexity and other things, what you're going to do is you're just going to take a question from the internet, right? So just going to take a question from the internet and you're going to implement it, right? So you're going to implement your own version. Your friend is going to implement his or her own version, right? So yeah. So say this is a question and n is the input to this question, right? So n is the input to this question. Say you're going to write this piece of code. So what you're going to do is you're going to run a for loop from 1 to n, right? I'm going to do some operations here, which we can ignore it, right? Okay, so this is one way to implement this, right? What is your friend doing is, so he is also starting a for loop from 1 to n, but for some reason, he has left this for loop empty, meaning there is something inside this for loop, it is just going to run, right? So yeah, so this is the difference between you and your friend, and he is also going to write the similar logic. So this one empty for loop, and he is going to again start a for loop, and he is going to do the same thing which you did, right? So even though both of you, both of you are going to do the same thing, only thing is your friend has kind of left a empty for loop before this, right? So this is also n is the input for your friend also, and both of you will be getting the same output, right? Because you both are kind of writing the same logic, right? Okay, so this is a piece of code and this is the premise. So you're taking a question from the internet, you're writing your own version, your friend is writing his or her own version, right? And then you're going to compare the time complexity, right? So that's what you're going to do, right? So yeah, so now tell me, how many iterations your piece of code is going to take, how many iterations your friend's piece of code is going to take. Let's forget the time complexity, let's focus only on the number of iterations. So here, even though it's empty, right? Even though it's empty, this will be executed n times, correct? And there is one more n. So how many times your friend's code will be executed, right? So computer doesn't know. Computer is not smart enough to understand that it is empty or something, right? So it just knows, okay, I'm going to it's just going to know, okay, I'm going to there is a for loop here, I'm going to run this. So it is not smart enough to know that, okay, it's empty or something, right? So it is going to take 2n iterations. So your code is going to take n iterations. Your friend's code is going to take 2n iterations, right? So yeah. Okay. So now, what is time complexity saying is both of these are going to have O of n. Both of these are going to be given as O of n. So what is the first rule of time complexity is you can ignore the constant terms from it, right? So you can ignore the constant terms from it, right? So that is the first rule of time complexity, right? So now you can ask, right? So O of n means it is not going to take n iterations, but this is taking more than n iterations. So this means that this is wrong, right? So if you see this part alone, this part is fine. This part is straightforward. If you see this part, O of n means it is going to take only n iterations, right? But this 2n is 2 times n. But how can we ignore this constant terms? Then this O of n will become kind of, you get the idea, right? So O of n will kind of become against whatever it is saying, right? So yeah, so this is the basic thing of time complexity. So first rule is you can ignore the constant terms, right? So for now we need to know why did they come up with this kind of an idea, right? So that is the basic thing we have to can you make the chat private? Okay, sorry. Participant can chat with, okay. So now I think you can chat only with me. Okay, sorry for that. Okay, so I made the chat private, so you can only chat with me. You can't put it in everyone, I guess. Please do check and let me know. Okay, so now we have to see why did they even come up with this, right? So why did they even come up with this, right? So why can't we give us O of n, and why can't we give it as O of 2n, 3n, 4n, 5n, right? Okay, so this is where time complexity kind of gets trickier, right? So first we have to understand what was the motivation behind this time complexity, right? So what I mean by motivation is, what was the idea behind coming up with this time complexity, right? So the first thing is time complexity was not found out to find the exact time or exact, uh, you know, you know, kind of, exact number of iterations or something, right? So that was not the idea behind this. So sorry, I think my internet is bad. I think, is it breaking? Okay. So the main idea of time complexity is not to find with, yeah. So as I said, it was not, kind of find something very, accurate or something, right? So what was the main idea behind this time complexity, right? So to understand this, we'll take one example, right? Say there is one question, even the previous question we solved during the previous session, right? So say we had 4 approaches, but say there were 100 or, or 50 approaches for that, right? Just some example, you can't, kind of name the question is having only 50 approaches or something, right? So, okay. So what we are going to do is say a question is having 50 approaches, right? So what is this time complexity saying is, first, so time complexity is kind of a first way to segregate these 50 approaches, right? So given these 50 approaches, time complexity will say, okay, X approaches are better than, so say these approaches are having 3 different, buckets, right? What I mean by bucket is, X is the time complexity, is less than Y, is less than Z, right? So X is the least time complexity, which means that it is the most efficient, right? So X is the most efficient, Z is the least efficient, right? So time complexity's idea is not to find the best out of these 50, right? You can't find the best. The reason being, it's not like there is one approach which is always the best for a given question, right? So how does usually it works is, for a given question, there'll be a bunch of approaches which are more efficient, right? Among these approaches, which is better, you have to figure it out, right? So time complexity's idea is, among these 50, I'll say which all are most efficient among these 50, right? So say there are bucket. What I mean by bucket is 50 approaches, say 10 approaches fall here, 20 approaches fall here, and 20 approaches fall here. So what is time complexity going to do is, among these 50, 10 are more efficient. Then, then 20 are, kind of moderately efficient, and other 20 are really bad, right? So what is time complexity going to do is, it is going to take out all the X from Y and Z, right? So that is the basic idea of this time complexity, right? So that was the motivation behind time complexity. So right now what they thought was, if time complexity is kind of accurate, what will happen is, you can't classify into lesser number of buckets, right? So what does it mean? Okay. So let's take this example itself, right? So this question itself. So this question, you solved it in n instructions. Your friend solved it in 2n. Someone would have solved it in 3n. Someone would have solved it in 2.5n. What I mean by 2.5n is, they ran 2 loops and then they ran for half a time, right? And someone ran it in 4.5n. Someone did it in half n. Someone did it in 1/4 of n, right? So what is time complexity going to do is, so say time complexity is very accurate. So what will happen is, say there are 50 approaches, right? So all these 50 will be having 50 different, time complexity, right? So that is the basic idea, behind this time complexity. So what they wanted to do is, let's not be very accurate. Let's be moderately accurate. Let's use this time complexity as a first way to classify, right? So this uses time complexity as a very high level. Let's classify it based on this. And among these classification, there'll be a handful of it, right? Say among these 50, only 10 were useful to us. So anyway, you're going to write efficient piece of code. I'll say why we need a efficient piece of code. But among these 50, this 10 is kind of efficient, right? Among these 10, which one to choose, time complexity is not going to give you, right? So that's the trade-off they took, right? Or else what will happen is, say 50, if time complexity had been very accurate, say this is O of n, this is O of 2n, 3n, everything, then what would happen is, there'll be 50 different things. So you don't know which one to choose, right? So which one is better? Choosing one among 10 or one among 50, right? So you get the idea, right? So time complexity not being very accurate here is going to help you, right? You get the difference, right? So if they had been very accurate, you would have had 50 approaches. So you have to choose one among these 50. But if time complexity is not very accurate, it is going to take only 10 out of these and going to give one. So which was easier for you, right? So getting one from 10 is much easier than getting, one from 50, right? So is everyone clear on what is the motivation of this time complexity? So what they decided was time complexity will be based on only the input, right? If input is n, it will be based on that n, right? If input is n comma k, it will be based on that n comma k, right? Because as the input increases, the time is going to increase, right? So that's the basic idea behind this time complexity. For not for all the cases, most of the cases, if the input is increasing, the time is also going to increase, right? What I mean by time is the number of executions here. Okay. Again, when in a time complexity, whenever they say time, it's not the time we see in real world. It's the number of executions or number of iterations, right? Okay, so now we'll see one example where time complexity is actually helping, right? So I told, you can ignore the constant terms. So here, what is time complexity saying is, oh, if a program is taking n iteration, 2n iteration, 3n iteration, 2.5, 4.5. So among all these numbers are constants, right? So these numbers are constants. So what is time complexity saying is, you can ditch out these constants and give it as O of n, right? So it will not be accurate, yes, but what will happen is all these 10 approaches will fall into one bucket, right? Say there are some other approaches, right? Say there are n square, 2n square, 3n square. All these things will fall into the second bucket, right? Say there is n cube, 2n cube, 3n cube. All these things will fall into the third bucket, right? So time complexity is not very accurate. So it will give it as O of n square, n cube, because it is going to remove the constant, right? So what you can do is you can completely ignore this n square and n cube and directly see what is the O of n approach, right? You get the idea, right? Among these O of n, which is better, time complexity is not going to help you. You have to figure out based on the input. So what is time complexity saying is, okay, I don't want to find the best. I just want to, do a very high level investigation and give it to you. So what is this high level investigation going to do? It is going to take a bunch of good approaches and give it to you, right? Among these good, which is even more better, you have to figure it out, right? So this is the basic motivation of this time complexity. So everyone clear till this point? Anyone having any doubts before we move on? Okay. So if this is clear, right? So we'll see a case where actually time complexity is helping. Okay. So yeah. So say let's just take another how to find 10 among these 50. That's a very good way, right? Okay. That's what we'll be seeing now. Okay. Okay. So now let's just see, right? Same thing. The same question is being taken from the internet. You are A and your friend is B, right? So both of you are going to write your own piece of code because you guys have already studied what is time complexity, right? So again, right? So you're going to run a for loop from 1 to n, right? And it is going to finish here. So what is your friend doing is, say he doesn't know a very good way to do this. So he's going to use a nested loop. So what is a nested loop? A for inside a for, right? Right. So this is the basic difference between A and B, right? So A is using only one loop, B is using a nested loop, right? Not two loops independently, nested loop. Okay. So how many iterations A will take? How many iterations B will take? Just the iterations, not the complexity. We'll come back to the complexity. So A is going to take n iteration. B is going to take how many iteration? Okay. So how to find the number of iterations in B? So it's very simple, right? So how many times J will be running when I equal to 1? When I equal to 1, J will start at 1 and go till n. So n times. When I equal to 2, J will again start at 1 and go till n times. Likewise, I itself is going to go n times. So it's n plus n plus n plus n times. So what is 5 plus 5 plus 5? 5 times 5 square. What is n plus n plus n times n square, right? So this is going to take n square iterations. This is going to take n iterations, right? So till this point, is everyone clear? So someone was asking, so how do we differentiate the 10 among these 50, right? So 50 approaches I have, how do I know that this 10 are better, right? So here, if you see, right, is there any constant terms here? So what I mean by constant terms is there any term which is not going to change if the input is changing, right? So if n is changing, the number of iterations is going to change, right? So if n is between 10,000, it will be running 10,000. If n is 5, it will be running 5. If n is 10, it will be running 10 times. Again here, if n is 10, it will be run 100 times, right? Because n square. If n is 20, it will run 400 times, right? So yeah. So if you see, it is changing only based on the input, right? But if you take an example like 2n or something, this 2 is independent of the input, right? If the input is changing, this 2 is not going to change. So this is called a constant. So like in English term, what is constant? It is not going to change. Likewise, this 2 is not going to change here, right? So here we don't have any constant. So we don't need to ignore it, right? So now you understand, right? Say this is the question and you have two approaches, right? Which is a better approach here, A or B? Okay, so A is a better approach. Why? Because it is going to take lesser number of iterations, right? So that is the basic idea here, right? So now you can ask, we can also have 2n as a separate entity, right? So what is the harm in having it, right? So I'll say what is the harm in having it, right? So what will happen is, say in these 50 approaches, half or 25 are O of n and 25 are O of n square, right? So you can directly ignore these 25, right? But if you had, if time complexity were accurate, what will happen is there'll be 50 approaches having different time complexity. So it is as good as not having time complexity at all, right? So it is not going to help you in any way being accurate, right? So that's why the time complexity is not like, so how do they pronounce this time complexity is order of n. What I mean by order of n is it's not actually n, but in the order of n, meaning, so say this is a graph, right? So n will look something like this, right? N square will look something like this, right? So it will increase as x increases, y will increase drastically. So y is the output, right? X is the input, right? So this is the basic idea of this time complexity. So they don't worry about 2n and all. So what will 2n happen is it will be kind of very very close to this n. It will be looking something like this 2n. 3n will look something like this, but it will never be n square. You get the idea, right? Unless it is n times n, it will not be n square. N times n is a separate entity itself. You can't ignore this n because n is not a constant here. Say this for loop, right? Say you're writing this for loop n times below each other. So it will be n into n, right? Because n plus n plus n plus n times, right? So now you can't ignore this n because n is not a constant here. You get the idea, right? So yeah. So what main idea of this complexity is I don't want the constant terms because it is not going to change based on the input. So what is the main idea behind this is a code's complexity will increase if the input is increasing, if the number of iterations is increasing. That's the part I'm interested in because that's the part you can reduce, right? These constant terms is not going to help you much, right? So that's the basic idea of this time complexity. So that's why it's okay to ignore the constant terms. So is it clear? So is everyone convinced on why we can ignore the constant terms? Yeah. So how the number of iterations will improve based on the input? Take this example, right? So this for loop. If n is 10, how many times it will run? 100 times. If n is 50, how many times it will run? 50 into 50, right? So it is being affected based on the number of inputs, right? I mean the value of the input. Is it clear? Anyone having any doubts, or should I repeat any part of? Okay, so I hope everyone is clear and convinced as well, right? So yeah, you can just learn this time complexity and just learn this why you can ignore the constant terms, but you have to understand uh, uh, why we are doing this, right? So that is more important. So whenever you learn anything, not just in computer science, anywhere, if you learn the why of it, it will be easier for you, right? Yeah. Okay. So this is the first part where, given the piece of code, you don't worry too much about the, accuracy of the time complexity. You just try to find it in order of something. So what is it? What does it? So this term order is very important. So whenever they say time complexity, they'll be in order of n, in order of n square. So what does it? What does this order of n square mean? Is it can be 2n square, 5n square, 10n square. It doesn't matter. But it is n square. It is kind of following the path of n square, right? So what is the order of n? It can be 5n, 10n, 15n. It doesn't matter. You can ignore the constant. It is just that it is very close to n, right? That is the terminology order means, right? So that part is very important. So if you have seen any MIT lectures or Stanford lectures, they'll be like, this is in order of n or order of n square or order of n cube, right? So whenever you see any time complexity in anywhere else, you will not find any constant terms as such. So yeah, so this is the basic idea. The thing is, we don't want anything accurate. We just want to have lesser number of classification. Lesser number of classification, we can classify more code into a specific classification. Among these 50, you can just, so here the classification is only three, right? X, Y, and Z. So you can ignore Y and Z and focus only on X. So you reduce the number of possible useful solutions to 10, right? So yeah. So what does it mean in an interview? In an interview, say you're coming up with, say the interview, say there is a question one. Okay. This question one's most efficient complexity is O of n, right? So you can do it in two instructions, 3 and instructions, 5 and instructions, half and instructions, 0.25 and instructions, anything, right? It's okay to do in any of these because all these are going to have O of n complexity, right? So in interview also it is going to help you, right? If they really want only this 0.25 n, then it's not possible. It's even more difficult, right? So that's why they just want to match the complexity and not the approach, right? Because if you try to match the approach, it becomes too narrow, right? So yeah.
Hi,
Okay.
I have a query.
Yeah.
So if the in some cases if n value is fixed, and there are two methods like n square, 1n square is the one approach, and here 6n is another approach. Then n square will be better than 6n, right? When n value is lesser.
If n is lesser, it becomes a constant. Yeah, it will be, but usually you don't worry. You see it for a very large input. Say if n is equal to 10,000 or something, 10 power 5 or something, right? So you don't know, right? So you don't know Netflix is going to have 5 million people, right? You can't do it for 5 people, right?
Yeah, but sometimes there may be the case that n square will be better than n O of n also.
Yeah, but right. So it will be better. But if you see in a very holistic level, right? So for few cases it will be better. Say
Okay, okay.
5n, it will be looking like this. But n square, maybe it can go down. It can go down, but it will quickly go up, right? So it will not go as fast as, I mean, it will go very fast compared to 5, right? So till certain point, yeah, maybe this point n square will be better. But usually they don't say it for very smaller inputs or something. Usually they say it for, millions or, very high input kind of a thing.
Okay. Okay.
Okay, so I hope everyone is clear on this first part of it, which is you can ignore the constant terms, right? Okay. So this is the first rule of time complexity, right? So what is the second rule? So second rule is, say in a given piece of code, you can divide it into few parts, right? So some part will be having some complexity, other parts will be having other complexity, and so on, right? So or not complexity, the number of instructions, right? Say there is a piece of code, right? And you divide it into 3 or 4 parts, right? So I'll just put it as 4 parts. So you divide it into 4 parts. The first part is going to take n instructions. Second part is going to take n square instructions. Third part is going to take n power 4 instructions, and the fourth part is going to take n cube instructions, right? So n is the input to this program, right? Okay. So say there are 4 parts to it, right? So among these 4 parts, which part is slowing down the entire piece of code? The first part, second part, third part, or fourth part? So among these 4 parts, which is slowing down the entire code execution itself? So think of this like a relay race, right? So we have 4 parts, four people running, right? How 4 parts? So among these things, which is actually very slow, right? So the third part is very slow, right? So say, how do I know? Say n is equal to 10, right? So this is going to take 10 iterations, 100, 10, 10,000. This is going to be 10 cube, right? So among these, this is the slowest part, right? This is going to take the total number of many iterations compared to others, right? So this is actually kind of slowing down the entire piece of code. Right. So think of this like a relay race, right? So in a relay race, the person who is running the slowest is the one who is going to, who needs a lot of, practice or something, right? Or who needs a lot of attention, right? Same case for a time complexity kind of focus only on the slowest piece of the code, right? So compared to this n power 4, n cube, n square, and n are not at all useful. So what is time complexity saying is, if you have other number of terms, you can ignore this, right? So among these 4, n power 4 is the one which we are going to focus on, right? So what is time complexity saying is, you can ignore the lower terms, right? Again, it is going to help us like our previous case, because in some other case, it can be n power 4 plus n by 2, or not n by 2 is not possible because it ignore the constants. Say there is n square and n cube alone, right? In some other case, someone is writing n power 4 plus n cube plus m. They are not having this n square term. In some other case, someone is having n power 4 plus n square alone, right? So all these things will be having the same complexity of n power 4, right? So you get the idea, right? Again, you're going to reduce the number of classification, because at the end of the day, say if you're doing some optimization, right? Say you're doing some optimizations to this piece of code, where will you first do the optimization? Definitely the third one, right? That's the only thing which we really want, right? So time complexity is going to focus only on the part which is the slowest, right? So yeah, so this is the second part. I think this part is much more obvious than the previous one. So second rule of time complexity is, you can ignore the smaller terms. So what I mean by smaller terms is, so here n power 4, compare to n power 4, n square, n and n cube are smaller terms, right? So you can just write it as O of n power 4. Okay, so take this piece of code and let's just say that this pieces can be divided into 4 parts, where each part is going to have some number of iterations, right? So first part is going to have n iteration, then n square iteration, n power 4, and n cube, right? So among these 4 parts, which is slowing down the entire piece of code. So someone asked me to explain again, so I'm just explaining them. So which part is slowing down the entire piece of code? N power 4 is going to slow down the entire piece of code. Say if you want to do some optimizations later, what I mean by optimizations is you're going to make the program better. Which part you'll be focusing on? You'll be focusing on the slower part, which is n power 4, right? So that's the only thing time complexity is also going to focus on. You get the idea, right? So yeah. So time complexity, what is time complexity? What is O of n power 4? The order in which the code is going to go is n power 4, right? So that's the basic idea of this. If it is plus n cube and n square, these are all small quantities compared to n power 4, right? So if you take n is equal to 10 power 5, 10 power 4 is something like 10 power 5 into 10 power 5 plus 10 power 5 into 10 power 20. So compared to 10 power 20, 10 power 15 is very, very less. 10 power 20 is very, very, very high than 10 power 15, right? So usually it's not a very good way to do this, but you get the idea, right? So we focus only on the least efficient part of the code. And that is also going to help you in reducing the number of classifications, because all these people, someone is doing n power 4 plus n cube plus n square, someone is doing in n power 4 plus n, someone is doing in n power 4 plus n cube, all sorts of possibilities. Everyone will be having only n cube, right? So yeah. So, yeah, so this is the second part. So first part is you can ignore the constant term. Second part is you can ignore the smaller terms. Okay, so with this, the theoretical part of time complexity is closed, right? So there are 2 more things which you want to cover before we move on to questions. But yeah, theoretically, this is what is time complexity. So what is time complexity? Given a piece of code or given a question you want to find, or given few bunches of code you want to find, what are all those approaches which are efficient, right? What I'm saying, why I'm saying is what are all those is it's not one, it can be many, right? That's the main idea of this time complexity. It's just going to classify only the best ones, right? Among these best ones, there can be multiple small here and there optimizations which you have to take care. Time complexity is not going to help you, right? So it has 2 things. One is it's going to ignore the constant terms. Why it's going to ignore the constant terms? Because if you start adding the constant terms and start making it more accurate, it is not going to help you, right? What you want at the end of the day is you want to have lesser classification. What I mean by classification is if there are 100 approaches, it can be classified into 3 parts. It is easier for you, right? You can just focus on the most efficient part of it, right? If it is very accurate, then everything will be its own classification, right? If there are 100 approaches, there will be 100 classification, which is not going to help you again, right? So that's why it's more like a first level investigation. Second level investigation is actually selecting the best out of best, right? That best will change based on the application. So sometimes it's okay to make the code slower to make it more understandable. Sometimes you want the code to be faster even though the code is not looking really good, right? So those kind of things. You get the idea, right? So second part is, say there are multiple small pieces in the code, especially in the bigger code, right? So you focus on the piece which is slowing down the entire piece of code. Why? In the future, if you want to do some optimizations, you focus only on that part, right? That's the obvious thing, right? So there's no point in optimizing the faster parts, because slower part is the one which is anyway going to slow down the program, right? So there's no point in same thing in a relay race. Even though the faster guys, if you make them even more faster, it is going to help you, but you get the idea, right? It's not going to help you much unless you make the slower person faster. It's not going to help you much, right? So same thing. So this is the basic idea of time complexity. So any doubts in this overall? As I said, right? So don't worry too much about substituting numbers or time there, right? because it's not having a unit for a reason, right? You can't give a unit to it. So once you add the time or numbers or something, it is going to the main crux of it is going to dissolve, right? The main idea is it's not accurate. It's more like an abstract concept. Yeah. Any doubts?
Can you mention last thing once again, because you were mentioning about making the slower person faster or faster person faster.
Slower person faster. So who is the slower here?
So we need, you were saying we need to try to make a slower person faster.
Right.
So what is the advantage among it? Because we have already a faster algorithm. Why we need to concentrate
No,
on
no, no.
slower one?
This is a single code, right? This is a single code for a single question. So among these codes, there are 4 parts, right? Say first you just, write a for loop. Then you do some nested for loop and do some other thing. Then you do some 4 for loops and do some other thing. Then you do some 3 for loops and finally give the answer, right? So you'll be giving only one answer, right? Say if you're going to optimize this entire piece of code, which is the first part you'll be trying to optimize, right? So that's what I was saying. It's not like 4 different pieces of code. You get the difference?
Not so clear.
Okay. So this is a single piece of code, okay? Say you're writing a for loop here and finishing it here. Say you're writing one more for loop here. This is a nested for loop, right? So if you see, this is going to take n instructions, is going to take n square instruction. Say in future, you find out that, okay, I'm going to optimize this piece of code. I'm going to try to optimize, right? It's not like this for loop is, this code you have written is like kind of the optimized, right? So which part you'll be first trying to optimize? The first part or the second part?
Here only I am thinking I need to concentrate on first one only, because
Okay.
since it is already better, we will try to make it the whole question better rather than making the concentrating on the second one.
Okay. So let's just take that. Say n is equal to 10 power 5. Okay. And it will take 1 second to do 10 power 5 instructions. So n is 10 power 5. It is going to take 1 second to do 10 power 5 instructions, right? So how much time this piece of code is going to take? 1 second, correct?
Okay.
Because n is 10 power 5 and your compiler can do 10 power 5 instructions in 1 second.
Yeah.
So this first part will finish in 1 second, right? So
Yes.
how much time the second part is going to take?
10 power 5 square.
Okay, so let's just do some basic mathematics, right?
Okay.
So 10 power 5 instructions is going to take 1 second, right? So here you have n is equal to 10 power 5.
So here it is 10 power 10.
So it is 1 second. So here how many instructions will be happening if n is 10 power 5?
10 power 10.
10 power 10 instructions, right? So how many seconds it will take? This is cross multiplication, correct? So 10 power 10 into 1 by 10 power 5. So how many seconds?
10 power 5.
Yes. So this piece of code is going to take 10 power 5 seconds, which is 28 hours. So which one do you try to optimize now?
Yeah. Okay. Second one.
Yeah, you get the idea, right? So this is the basic idea. So
Okay.
n square is very bad that there's no point in optimizing. Say if we're doing this as a 0.5 seconds, there's no like you do get something, but it's not like a something. So if you can make this 1 second, then the entire code is going to take maybe 2 seconds, right?
Yeah. But if we have a better one, first one approach is better one. Why we want to use second? Why we
No,
why we
this
want?
is a part of the same code. Same
Okay.
code.
Got it. Got it.
Yeah, you get the idea. Same question. Like it's not 2 different questions
Sure.
or 2 different approaches. Same approach.
Thanks.
You get the idea, right? So this is why we focus only on the most,
Yeah, clear.
worst part of the code, right? So yeah, and this is why time compressor is also going to focus only on this. Right? So now is everyone clear? So everyone clear on how we got this 10 power 5 seconds? 10 power 5 seconds is 28 hours. You can Google it. So which means that if you run this code and if n is 10 power 5, which is not even a bigger number. So 10 power 5 is what? 1 lakh, right? 0.1 million, right? 0.1 million is not even a bigger number. Like you can do this every time. So if you run an n square algorithm on 0.1 million, it is going to take 28 hours. So yeah. So this is a level, as I said, right? So time complexity is going to deal with a very high level, right? This is the level at which it is going to deal with, right? Not like 2 seconds, 3 seconds algorithm. Say if it is taking 2 in iteration, it is going to take 2 seconds. So compared to 2 seconds, 28 hours is anyway really bad, right? So that's why it's okay to ignore these constant terms, right? So that's the basic idea of time complexity. Like it is focusing on a very high level that these small things does not even matter. Yeah, 27.77, close to 28 hours. Right. So yeah. So if you remove the constant term, the exact time will not be same, but it doesn't matter because you're running 2 times, it will be 2 seconds, right? And that's why I said, right? So it's not a very good way to equate time and this thing because time is accurate, absolute value. Time complexity is a approximate order kind of a value, right? That's why it's not having any terms, right? So yeah. Okay. So what we'll do is we'll have a 5 minutes break or even 8 minutes break. We'll meet at 10:30. So we'll come back and see 2 more topics, and then we'll try to solve few questions so that you can start, coding in code kata, right? So yeah. So we'll meet at 10:30. I also attach the feedback form. So you take some break and then fill in the feedback form, and we'll meet at 10:30. Okay, so yeah, we'll get going. Great. So I just have to cover two things. One is space complexity, right? So before that, we'll cover what is constant time complexity, right? So constant time complexity, right? So what is this now constant time complexity? So far, right? So we have seen given the input, what is the complexity, right? So if n is the input, if you're running one for loop, it is O of n. If n is the input, if you're running nested for loop, it is O of n square and stuff, right? So yeah, right. So this is what we have been doing, right? So this need not be true for all the cases, right? So there can be some cases where if n is the input, you don't run any loop at all. You just do some mathematics, right? Say if you want to find the value of 1 to 1 plus 2 plus till n, it is called summation of n terms. Right? So either you can run a loop from 1 to n and do the sum, or you can use the formula, right? So what is this formula? N into n plus 1 by 2, right? So if you see, right, if n's value is saying, say this is one instruction, right? So what is this instruction? You just do multiplication and dividing by 2, right? This is one instruction, right? This is considered to be one instruction. Is the number of instructions changing based on the value n? If n is 100 or n is 1000 or n is 500, is the number of instructions changing here? What I mean by that is, if n is 100, are you running this 100 times? If n is 10, are you running this 10 times? If n is 5, are you running this 5 times? Whatever be it, it is just being running one time, right? So this is the constant time complexity. What does it mean is the number of iteration is not dependent on the input, right? So n's value will change, but the number of instructions n is going to number of instruction n is going to take care is less, right? I mean, sorry, the number of instruction n is going to do is same. Only the value can change. You get the difference, right? So this is called constant time complexity, right? So there can be cases where whatever will be the input, the number of instruction will be constant, right? So how do I represent it? It is always O of 1. Even if you do 10 operations, say you run a for loop where you start from 1 and go to 10, what will be the input? If n is the input, uh, the for loop always runs for 10 times, right? So even in these cases, it is constant, right? So this is represented as O of 1. So you get the difference, right? So in some cases, whatever be the input, the number of instruction is going to remain constant, right? One case is here. If you use mathematics, it is the number of multiplication and number of division you do is only once, right? The number can be different, but the number of multiplication or number of iteration you do is only once, right? So whatever be the value of input, the number of instruction is not going to change that, right? So these cases are called constant time complexity. So how do I represent it? It is O of 1, right? So what all things can fall into O of 1? Addition is O of 1 because the addition can do the value can change, right? So it can be 5 plus 5 or 10 plus 10. It doesn't matter, right? But the addition algorithm or addition operation itself is being executed only once, right? It is not dependent. If n is 100, we are not doing 100 additions. If n is 10,000, we are not doing 10,000 additions. Addition is only once. Maybe the value can change, right? Value doesn't matter to us, right? The number of instruction only matters to us, right? So yeah. So this is called constant time complexity. So any doubts in this? Not only for addition, right? So even for subtraction, even for multiplication, even for division, or even if you do, we did that XOR, right? XOR is also, one time. right? XOR is also O of 1. You get the idea, right? Because say if you are running a for loop, right? I is equal to 1 to 10, 1 to n, right? And you do an addition inside this, right? So this addition will be done n times, correct? So this is O of n, right? But if you do a formula n into n plus 1 by 2, right? If you do a formula n into n plus 1 by 2, the multiplication and division, multiplication is done once, division is done once. So there are only two operations involved, right? Which is O of 1. You get the difference, right? So here addition itself is going to take, addition is one operation. It is going to be repeated the number of times you want, right? So yeah. Now is it clear? So you just see the number of operations. Don't worry about what it is doing. Anyone wants me to repeat again? Right. So yeah. So this is called constant time complexity, right? So we'll come back to it, right? We'll see some questions. I don't know. I don't think we can do it today because we started late, but we can see some questions and then we can see what is constant time, right? So far, whatever we are seeing is called time complexity, right? So we had two rules. One is you can ignore the constant terms, ignore the lower terms, and then we saw what is constant time complexity, right? So these are all called time complexities, right? So there is something called space complexity as well. So if you think, right, so there are only two main components in a computer. One is the processor. One is the memory. Memory is RAM, right? Not the hard disk, the RAM, the random access, the one which is being used while the execution, right? Okay. So what is processor? What is processor doing? It is going to execute instructions, right? So whatever time complexity you're going to do is more of related to processor, like how the processing you're going to reduce. If you reduce the number of processing, the time complexity is going to reduce, right? Or if you reduce the time complexity, the number of processing is going to reduce, right? So there is something called space complexity as well, right? Space complexity as well. Because if you think, right, so this RAM is not unlimited. You can't keep using RAM forever, right? So there is also a limit for that, right? So based on the computer, it can change, but you get the idea, right? So like processor will also be having how many hertz it can run, right? What is the number of hertz? It can run like 2.2 gigahertz or something. That many instructions in 1 second, right? That's called hertz, right? So if you are heard clock speed, right? So that's the basic idea. Likewise, memory will also be fixed, like 8 GB or something, right? So you can't keep using it, right? So there is something called space complexity as well, right? Same idea, this same notation we go, same everything, right? This will say in which order it is the space is being used, right? Again, order, right? Once I say order, these two rules also apply here, right? So say for an example, for a given n, you are creating an array of size n, okay? Array of size n, right? So this is called O of n space, right? If you have 10 arrays of size n, then it is O of n again, O of n space. Because 10 is a constant here, you can ignore the constant terms. You can just give it as O of n space, right? Same thing, same idea, same notation. Just that in time complexity is the number of instructions. In space complexity is the amount of memory it is taking, right? So inside this, it can be integer, string, it can be anything. Not string, integer, character, boolean, anything, right? String, the length of the string itself depends, right? Say if n is the input, right? N is the input, and you write a string of size n, then this is O of n space, right? Even though this is a single string A, the size taken is based on the input, right? Again, right? So whatever is happening based on the input, that will be counted, right? Same as time complexity, right? So this is the basic idea of the space complexity. And when can n square happen? N square can happen if you are creating a matrix of size n, right? So there can be some cases where you want a matrix to store. So if n is the input, you create n cross n matrix. So there it will be O of n square space, right? So there it will be O of n square space. right? Here also there can be a case where constant is happening, right? Say if n is the input to the program, right? Whatever be the input, you just create a variable a and assign a value 10, right? So a is some memory which is going to be stored in the RAM, right? So a is some memory, right? But this is one memory in RAM, right? But if n is changing, the number of memory being used is going to change. So say for a program, n is the input, right? And we have only one variable, a. Okay. If n is changing, will you be creating more variables? What is variable here? The memory, right? Memory space you are going to use, right? Right? So yeah, so this is called constant space complexity. Again, the notation, everything is same. If it is time, you say time. If it is space, you say space. That's the only thing. So constant space complexity, constant time complexity, O of n time complexity, O of n space complexity. Only the change will name will change and the idea will change. There, the idea is the number of instruction. Here, the idea is the amount of space, right? Amount of memory allocations used, right? So that's the basic idea. Again, the order, the two rules you had, everything matches here, right? So why do you need this? As I said, memory is not limited. I mean, memory is not unlimited, right? So it is limited. So you can't keep using the memory as well, like processing. So yeah, so space is also important. So any piece of code has two parts. One is memory and one is space. Sorry, one is a time complexity, one is space complexity. Right. So both of these are equally important. Right. So I think you can't compare these two. You can't say you can't compare space and time. These two are separate streams, right? Because these two are dealing with separate entities. One is dealing with processor, one is dealing with memory. You can't compare, right? So yeah. Again, O of 2n space will be, say, if you are using two arrays, it will again be O of n space only. Same, the two rules also matters. Same, everything is same. So what is 2n space? You create two arrays, right? So if n is the input, you create an array called A, you create another array of size called B, right? So this is actually 2n space, but you write it as O of n because you know the rules, right? So yeah. No, time and space will not be same, right? So time and space will not be same. It is dependent on how you write the code. So sometimes you can. So usually what happens is, say there is some n square time, but O of one space, right? The code you write. So you can kind of use this extra space to reduce the time. You can make it as n time and n space, right? So these two you can't compare. That's what I said. So these two are separate entities. Like they are because they are dealing with separate entities, right? So one is dealing with the instruction, one is dealing with the memory. Right? So you can't equate it. So you get the difference, right? And someone also asked one question where when which one is better? Nothing is better based on the thing. Which based on the application, you have to choose which is better. So sometimes you might be having more memory, but less space. Sorry, more memory but less processing power. In that case, you can choose algorithm where the time complexity is lesser, space complexity is okay or higher, right? Or if it is reverse, say you're having less memory but more processing power, you can use poor time complexity but better space complexity method, right? So yeah, so these two go hand in hand. You can't equate it, but these go hand in hand, right? You can never say one is always better than the other because these two are dealing with separate entities. So any doubts in this?
In space complexity, can you give any example like in time complexity we use a multiple? Someone can do it in 100 iterations. Someone can do it in inner loops like multiple n square iterations. Like that, any example in space complexity?
Same, right? So someone can do it using an array. Someone can do it without using an array by using one variable. Example. Just thinking, maybe you can see this question. Okay, same thing, right? So here, for same question, if you see, right? So we'll come back to the question which we saw. So given an array, all elements are repeated twice except one. You have to find that one, right? So that's the question we saw that day, right? So first we came up with the sorting algorithm, right? So what do? We sort it, right? We sort it. We start from the second index, I mean first index, and check whether that index and the previous index are same. If these two are same, then these are repeating. If these two are not same, you can just return it. So in that case, you will not use any extra space, correct? You'll just use sorting. You just sort it. So it will be O of n log n time O of one space. Why I'm saying you don't use any spaces? Because you are not creating any array or something. All right. So is everyone clear on the sorting? So sorting is O of n log n. I'm not going to cover it as part of DSNL Go. You can just Google and see why it is n log n, right? So no one is going to ask write a sorting algorithm or something, right? So no one really knows actually, right? That's the truth. But knowing why it is n log n is important. So you just go Google and just see why sorting is n log n, but you can't do better than this, right? So what is this log? So I have attached few homework problems here. So what you can do is you go through these problems and try to come up with the complexity. We'll discuss this in the next session, right? So that you have some practice kind of a thing. So coming back, sorting is n log n. N log n is worse than O of n, but better than n square, somewhere in between, right? So yeah. So and time is O of n space, because in that approach you don't use any extra memory, right? Maybe you can use one or two variables, which is fine, but you will not use an array or something which is dependent on the input, right? So is everyone clear on the sorting approach? Why it is O of n log n? N log n, I think you guys will read up on the internet. One O of one space, is everyone clear?
Yes, sir.
Efficient code should have good time complexity or space complexity. As I said, it depends. So sometimes you can come up with a better complexity but worse time complexity, space complexity, or vice versa. Based on the application, you have to choose which is better. Okay. So now we had second approach. Someone told that for this question, every element repeated twice except one. You can run two for loops, right? Nested for loops. So you start from one and go from the next and see whether these two are matched, right? If there is no match found, you can just return. That is the only thing which is not written, right? So that is one more way to do this. In that case, you use two for loops, right? So it is O of n square time. Again, here you will not be using any other space, right? Why you don't be using any other space? Because you're just going to compare and then return yes or no, right? So there'll be no spaces involved in. So is everyone clear on the second one? Okay. So third approach is we use the map where we store each number, how many times it's occurring, right? And then we went through the map and then gave the answer, right? So in that case, we would have used only one for loop. We go through the add in the map, we go through the array, add it in the map. So that will take off in time, and we go through the map to give the answer, right? But if you see,
Sir, sound is better.
now is it now is it audible?
Yes, sir.
Okay. So in the third approach, what you would have done is first you go through the array and then add it in the map, right? And you again go through the array and you go through the map and see which element is being repeated only once, right? So in this case, space will be O of n. Y means, say if the array size is n, okay? Every element is being repeated twice. So this map, there'll be n by 2 keys in the map, correct? Say if the array size is, array size is n. So there'll be n by 2 elements which is being repeated, right? Because every element is being repeated twice, right? So this map will be having n by 2 keys, right? So which is O of n space, right? Because you can ignore the constant term. So you get the difference. So in this case, time will be O of n, space will also be O of n. So is everyone clear on how we got this O of n space for the third approach? Because map will be storing n by 2 unique values, right? You can ignore the 1 by 2 constant, right? 1 by 2 is a constant here. You can ignore that. So it will be O of n. So anyone wants me to know how we get this n by 2? Okay, so let's just take an example, right? Say if 1 is being repeated twice, 2 is being repeated twice, 3 is being repeated only once, right? N is 5 here, right? N is 5 here, size of the value, right? So how many keys map will be having? So how many keys map or object will be having? So there'll be a key for 1, there'll be key for 2, there'll be key for 3, right? There'll be only 3, right? Value will be only be 2, right? Key should be unique, right? So is everyone clear on we'll be having only 3 keys? Why 3? Because every element is being repeated twice, right? So if there are n elements, that'll be n by 2 keys, right? So what is n by 2? N by 2 memory you're going to store, right? So you can ignore the constant terms 1 by 2. So it will be O of n space. So is everyone clear on this? How we got this O of n space? Map is nothing but a space, right? It's not like nothing is free here, right? So map is a space somewhere in the memory. So is everyone clear? Okay. So then we'll go to the most efficient approach. In this approach, what we did was we had one variable, right? We had one variable, and on the same variable we were writing on top of it, correct? Same variable we were doing, XOR on top of it, right? So what we'll do is we'll see the how to code it. I don't think I added the code for it. Right? So the fourth approach is the one which we saw, which is using XOR, and that will be having O of n time and O of one space, because we'll be having only one variable and during XOR on top of this, right? So let's just take this is the function, right? So a function solve, right? So you get the array, you get the value, you can just get the array, right? So here you'll be having XOR. So XOR will be 0 initially. So what you'll do, you'll go through this array, and what do you do? XOR is equal to XOR caret symbol ARR of 5. So what it will do? It will do XOR on top of it again and again and again, right? And then you return this XOR. So this XOR will be having the element which is not being repeated twice, right? So this is how the code would have looked like. So if you see how many memory we are taking, how much memory we are going to take. You're just having one variable, right? It's not dependent on the input. If array size is 100 or 1000 or 50,000 or 3000, we're just going to have only one XOR, right? So it will be O of one space, right? So is everyone clear on how we got this O of one space? So what will be the time complexity for this? So how many loops I'm running and what all things I'm doing? Right. So we are using one for loop. What is the array length? Say if n is the input, n containing the array size, you would have changed this as n, right? So here the time complexity is O of n time. So is everyone clear on this? How we got this O of n time and O of one space? Right. So among all these four, which is better now? So in our previous class, we told XOR is better, but can everyone see why XOR value is better? Why this fourth approach is better? Because one is having n log n, two is having n square, which is even worse. 3 and 4 are having the same time, but 3 is having extra space. 4 is not even taking any extra space, right? So this is why fourth is best compared. So this is where time complexity is helping you, right? So this problem, like 100 people, if you 100 people are doing it, 100 people doing it in different ways. That doesn't matter, right? Maybe they can do have one more for loop or something. That is fine. The main thing is, as long as you write a code where the time and space are what is wanted, then you're okay. Right? Say if you get the same question in interview, they'll be expecting you to solve it in O of n time and O of n space. Unless you come up with an approach to solve this, you will not be allowed to code. So that's what I meant by in an interview, this time complexity, they always expect the efficient approach. So is everyone clear on this? Right. So right. So if you are clear on this, then with this we'll stop this session. So next session we'll just go through the slide and try to try to solve three questions, right? And then we'll move on to the next topic. So I'll just add the slide link here. So this is a slide link, and yeah, so you can feel free to drop off if you don't have anything. So I'll close the session in another 1 minute. Okay. Yeah, thank you everyone for attending. I hope you understood things in this session. If you have any doubts in this session, you can also ask this in the next session. Right. So thank you everyone.
Can we leave, sir? Hello?
Yeah, so I think I have to drop off now. Can we, if you have any doubts, can we say it in the next session?
Session is over now.
Sorry.
Session is over now. Can we leave now?
Yeah, you can.